So please.
All right. My name is Junhao. First of all, I would like to clarify that I removed the explicit here in the title because my implementation is in implicit. The explicit I used before was referring to English term, so yeah, I removed that because of it might cause confusion. And thank you for Said for pointing that out. Right. Here is the outline. You can also see at the top of the screen the outline. So I'm going to start with heavy gas dispersion. So heavy gas is classified when the density is more than the density of air, which is 1.1, about 1.15, and they behave differently from neutral gases. Basically, they slump along the ground, and then they splat laterally, and they resist vertical mixing. So why do we need to analyze this? Because there are some critical industrial applications like ammonia bunkering or maybe just bunkering in general, LNG bunkering facilities as well, and then carbon dioxide for carbon capture and storage. So in order to predict all these safety zones, we need to have accurate modeling. First of all, the species transport equation. This is a fundamental conservation law for species mass derived from principles. And if you break them down, it's quite easy to understand. First, the first term here is the rate of change of the species mass. And then the second term here is the convection. And then we have the diffusion and finally reaction. So what is the J here? J is basically the molecular diffusion. Fick's law states that the diffusion occurs from high to low concentration regions. If you look here, this equation here, you can see the density times blah blah species mass again. This is basically the same thing here, rate of change of species mass multiplied by the diffusion coefficient. This DIM is diffusion coefficient, or in other words, mass diffusivity. We can also relate this to the momentum diffusivity or kinematic viscosity by using the Schmidt number. The Schmidt number is basically a ratio of momentum diffusivity to mass diffusivity. And then if we substitute all these equations in, we get the final equation. You can use both of these terms. It doesn't matter because they are the same thing. And then I'm going to introduce you to the turbulent diffusion. So in turbulent flows, the eddy motion provides additional mixing. In other words, in turbulent flows, it causes more diffusion and enhance the mixing overall. So this turbulent diffusion is typically much stronger than the molecular diffusion. And then turbulent diffusion, we have the same formula here, but here we use the dynamic viscosity, turbulent viscosity from the turbulence model, and the SCT here stands for the turbulent Schmidt number. So what's the difference between the two? Down here I used laminar Schmidt number, but I shouldn't really use laminar because it's really just the Schmidt number, but I used it here just to differentiate between the two. So the Schmidt number is just a physical property which is species specific. So each species had their own Schmidt number or diffusion coefficients. And then the turbulent Schmidt number is just to state the flow in general. So it's an empirical constant. So basically it has just categorize the flow in general. And then if we substitute all these equations in, the total diffusion flux is basically equals to the laminar molecular diffusion coefficient plus the turbulent diffusion flux. It's too many terms here. So if you add all this together and then you substitute all this into the species transport equation, you get a complete equation here. Same thing here, if we break down everything, the first term here is just the molecular diffusion, and then the second term here is just the turbulent diffusion. So in the standard reacting foam, we have this Y equation in the Y header file. You can see that it's the same, but they use the effective mu here. The effective mu is just basically mu plus turbulent mu. So what happened to the Schmidt number? So this implies that the Schmidt number is 1 for all species and turbulent Schmidt number is 1. This is what the reacting foam assumed. And this is all encoded in the Y equation. Yeah, so we're going to implement the diffusion coefficients here. And then next, the gravity term. Why this is important? Because the heavy gases, they rely on buoyancy to move in the flow. So in the general momentum equation of the Navier-Stokes, you have this. Everybody is quite familiar with this. And then you have the reacting foam U equation. You can see that there's no body force in here. Fg equals to 0. What we're going to implement here is the Bose approximation to use the simplified gravity term here. It's just the density minus the reference density times the gravity vector. So here we have a summary of limitations of the standard reacting foam. Mentioned just now, Schmidt number equals to 1. This is not correct for if you want to model heavy gas dispersion. And then there's no gravity term in the momentum equation. But in recent versions, the row reacting buoyant foam is introduced. I think it's in, version 18 and later. This changes everything because this row reacting buoyant foam solver is a enhanced buoyancy treatment. It has enhanced buoyancy treatment and it has improved density coupling and all these very complicated terms. I'm not going to explain this, but it still has one limitation, which is it still assumes that the Schmidt number is 1. So what we're going to modify here in the summary is that for reacting foam, we're going to include the mass diffusion term and the gravity term. And then for row reacting buoyant foam, we're going to just include the mass diffusion term since the gravity is already included. And then for validation, we are using a wind tunnel experiment conducted in Hamburg University in about 30 years ago. They simulated sulfur hexafluoride SF6 in a closed wind tunnel. So modifications. These are the files we're going to modify. For create fields, we're going to add the gravity and the row reference. This is for the Bose approximation. No change for the row reacting buoyant foam because there's already gravity. And then for U equation here, we're going to implement the Bose approximation itself. Again, here, there's no change because gravity is already implemented. And then for Y equation, we're going to implement the diffusion term for both solvers. And then P equation, we're going to introduce density relaxation. I'll explain more later about this density relaxation. But first, let's modify the reacting foam solver. So first of all, you know all these steps, copy, not to mess with the original solver, you copy to your project library, and then you copy the header files and the code files. The reason I do this separately is because within the original reacting foam solver, there's other subdirectories inside, like the buoyant reacting foam and the row reacting buoyant foam. So I only want the code and the header files for this. And once you copy, you update the make files to give it a name. I put here SC, which means Schmidt number, and then you rename the main file to your designated name. And then next, we move into the create fields. Here we add all this. First line here is just to say when you start the simulation, it'll just print out reading gravitational acceleration, which means it's successfully read the file. And then here we introduce G, which you need to later create a file in the constant folder. And then below that, we introduce the reference density. This row reference, this will tell the solver to go into the thermophysical properties file and then look for this sub-dictionary mixture and then look for its value. If there's no value specified, then a default value of 1.225 is used. This is the default value for density of air. And then you print out the reference density value. So later in the thermophysical properties, you'll need to put in this subdictionary and specify the row reference if needed. And then next, the U equation, we're going to introduce the Bosonist approximation. So you recall earlier that the U equation doesn't have the body force. Here we're going to add the body force by itself, just the Bosonist buoyancy term. That's the end of it. And then next we move on to the Y equation header file. Right at the beginning, before the loop begins, we add this line. This just tells the solver again to go into the thermophysical properties file and then look for the subdictionary. We're going to give it a name here, diffusion coefficients. And then next, create another subdictionary again. Here is the mixture. This is for the turbulence Smith number, SCT. And then if it's not specified, we're going to default it as 0.7. And then inside the loop species, but before the Y equation begins, we need to add these lines here, which basically tells the solver to read the diffusion coefficients for each species. So later in the thermophysical properties, you need to specify in the diffusion coefficients here. Oops, not here, sorry. Maybe later. Yep. And then within the YI equation matrix, scalar matrix, you can see we've added two lines here. The first one is the molecular diffusion, the Smith number, and then the second is the turbulent Smith number. This first term rho di basically means this, the equation before, and then turbulent Smith number is the turbulent viscosity times the divided by the turbulent Smith number. Yeah, both are user defined. And then finally, the P equation right at the end of the header file, we add the line rho relax for density relaxation. So why do we need density relaxation? This under relaxation, it limits how much the density changes per iteration. So basically the new density is calculated based on the old density times the relaxation factor, plus the relaxation factor times the calculated value minus the old density value. So in other words, it only applies 10% of the change if you put 0.1, or 0.3 means 30%, so and so on. So why is this needed? It's because sulfur hexafluoride has a density ratio of 5.9 to be exact, and these large density variation, they without relaxation, they create oscillations and instability and sometimes divergence. And with relaxation, you can make it converge easier. And then finally, we compile. This W clean here is just my habit. You don't actually need to use that. And then after you compile, you verify the installation, you type which reacting foam SC, and then you should expect this output here, which is the location of executable file. Next, we move on to the row reacting buoyant foam. Here's an overview. Since gravity is already included, we don't need to implement gravity, so we only need to modify the Y equation, add the density relaxation, and rename the files. Very simple. So same thing, we copy everything, but here, because row reacting buoyant foam, it's a variant of reacting foam solver, means it's a subdirectory within the reacting foam solver, so it shares some of the files with reacting foam solver. So here, since we are creating a new solver file here above, so we need to copy some of the shared files into our new solver. And then once you've done that, we can also copy the Y equation, by the way, because it's the same. We use the same Y equation, so you can copy the modified Y equation from our modified solver just now. And then once all that's done, we rename it as usual. And then the density relaxation for P equation header file, we go right to the end, and then we add row relax. And then once that's done, we compile and verify. So what has been modified so far is the diffusion term we've added for both solvers. For stability, we've added density relaxation for both solvers as well. And then for gravity, we've only added for reacting foam solver. And now we move on to validation and results. So this experiment is conducted in Hamburg University in 1995. It's in the wind tunnel, and then it's continuous release of sulfur hexafluoride down a 8.6% slope. The flow condition is quasi-quiescent, which means it's sort of laminar, but not really laminar, but with a Reynolds number of 15,000. So in our tutorial here, we're going to use laminar flow. No wind is present, and then below we have all the parameters here. Using this diffusion coefficient here, our computational setup, we're going to have a half domain with symmetry at the center. This is it has about 170,000 cells, and then it has a 70 millimeters diameter inlet. The gravity vector here we can calculate using trigonometry, and then these are the boundary conditions. On the ground we have a no slip wall, and then the top we have a slip wall. Outlet we have a pressure inlet outlet, and no wind. So the symmetry plane on the green block there, and also the sides. Yeah, this is the local refinement of the mesh. Here we have a single release source, and then symmetry on the green plane. Yeah. So this figure here is just an illustration, but the sensor locations it's exact, just for your reference. And then we move on to gravity file, which we need to create in a constant folder. As calculated just now, we have a 0.841 in the x direction and a negative 9.774 in the z direction, which means it's going down. If we check this, verify, it should arrive at 9.81 gravity. And then in our thermal physical properties file, we need to specify the subdictionary mixture, and then we specify all this row reference, turbulence mid number. This is only for turbulent flow, because in laminar flow this will be 0. And then the other subdictionary will be diffusion coefficients. We specify for each species here. Once that's done, we can run the file. So the case file structure here, you will be provided is as such. There will be all run script and all clean script, and then experimental folder, which consists of experimental data, and then a post-processing script, which produces the figures, and then your original setup cases for both solvers. Both cases, I mean. To execute, you simply run all run for single processor. If you want to run it parallel, you can specify, you need to change it, go into the all run script and change the parallel mode to true, and then you run it parallel. And to change the number of cores, you need to go into decompose product in the individual setup folders. So for 24 cores, it's about 15 minutes total simulation time. So results in symmetry plane, we can see that the reacting foam is not really good here. Row reacting buoyant foam has better agreement with experimental data, with about 20% under prediction in the near field. But in the far field, you can see it arrives at somewhat close to the experimental data. And then let's look at the transient behavior. This is for reacting foam. Severe under prediction everywhere, and then incorrect cloud arrival times here at the lateral far field, sorry. And then we look at the row reacting buoyant foam. This is much better. There's still under prediction in the near field, but in the far field, you can see it's very close to the experimental data. So in summary, the reacting foam solver underpredicts and has early arrival. This means that it has excessive mixing overall. And then for low reacting buoyant foam, it just has better agreement. So why does reacting foam solver underpredict? You recall that the only difference between the two solvers is the gravity. So if we go back to the Bosonist approximation, the approximation assumes that density differences are quite small. But in our simulation here, we use sulfur hexafluoride, which has a density ratio of more than 5, and this violates this assumption. And there are many more reasons of why this would be under predicting, but this is the only reason I can come up with for now. And then let's go to the conclusion and future work. So in summary, we've modified diffusion. We modified two solvers for the diffusion, and then we've added gravity for the reacting foam solver. And then we validated both solvers with experimental data. And then we found that the reacting foam solver underpredicted, and that the low reacting buoyant foam has better agreement. The key modifications here, you can see we've modified all these files. I'm not going to go into detail. And then for future work, this has been completed recently, but the next few slides I'll show the results of this. Basically, what I've done is that I've changed a singular release point of 70 millimeters plate into multiple holes within the diameter there. This will achieve a more realistic result and a more homogeneous flow overall. And then the other future work is the turbulence buoyancy coupling. This has also been done recently, but I won't be going through that here. So for the multiple hole injection geometry, you recall on the left side we have a single point release before. What I've done here is that I've made multiple holes there, the multiple hole injection to achieve a more homogeneous flow. To arrive at this, you need to refine the block. So the total number of cells, if I recall, is about 850,000 cells. This is because the multi-hole, all the little holes there are quite small, so you need very refined mesh. Oops, yeah. So this is the multi-hole results on the symmetry plane. You can see steady state. We've arrived very close to the experimental results. Very good agreement. And then on the transient, I'm not showing the reacting foam solver. This is just a low reacting buoyant foam. You can see a slight over prediction, but this is expected. And then, yeah, very slight over prediction. But this is better agreement than before. And yeah, thank you. That's it.